Hello, my name is Johnny Lin, and today I'll be talking about some issues when designing a class to teach programming to novice science and engineering students. In today's webinar, I'll be talking about two main categories of issues. First, some considerations when trying to find the right curriculum for such a course, and secondly, some considerations when looking to find the right class structure for such a course. So let's talk about the first topic, which is how to find the right curriculum for a course to teach programming to novice scientists and engineers. Now, the good news is there are a lot of great resources to help us to teach programming to any student. But the problem is that a lot of these great resources are not geared for novice scientists and engineers. A lot of these resources are extremely powerful, but they can also be quite complex, which makes them less accessible to novices. A lot of the traditional introductory computer science textbooks also take an approach that is not really connected to what scientists and engineers are looking for. The classic introductory computer science textbook sort of first line of code is to print hello world, which isn't really all that pertinent to what scientists and engineers do. And the problems in these textbooks tend to be abstract puzzles rather than real world problems. More particularly, they tend not to be real world problems from science and engineering. Finally, the curricular layout for these textbooks tend to be syntax focused as opposed to focus on the workflow of a scientist and engineer. Scientists and engineers generally are looking for using computer programs to solve science and engineering problems, not programming for programming's sake. Now, one approach in terms of curricular choice to get around these limitations is to use a textbook that focuses on scientific computing. But a lot of these scientific computing textbooks assume that you already know how to program. Their introduction to the syntax of a language is usually focused just on the syntax, not on helping a novice to be able to understand the constructs and structure that go into programming. And oftentimes these textbooks, they ramp up pretty quickly to sophisticated scientific use cases, for instance, numerical methods. So with those curricular issues in mind, let's take a look at our second main topic, which are the issues or considerations concerning how to find the right class structure for our course. Now in this section, what I want to do is to just look at a number of different class structures and see what the kind of strengths and weaknesses there are for each one of those class structures. So the first class structure we'll be looking at is the self-learning approach. And so in this approach, we ask students to teach themselves how to program using the internet, books, or other resources. One of the benefits of this particular approach is that it's convenient and self-paced. We can use this strategy with any kind of science and engineering course. However, this approach provides limited in-person guidance to the student who is just learning how to program. And in addition, it can be difficult to assemble a properly structured and paced curriculum, especially for a student who is brand new to programming. A second approach is the bootcamp approach. Now, in this approach, you have a maybe 1 week workshop in which you introduce the students to the use of programming languages to solve science and engineering problems. Software carpentry is probably one of the best known of these particular bootcamp curricula. They have a really well-developed curriculum and has been doing this kind of workshop for quite a while. Bootcamps, because they're quite short, are really convenient. You can spin one up without very much sort of infrastructure. You are also able to offer it multiple times over the course of a term. And boot camps utilize examples that are taken from science and from engineering use cases. But the downside of a boot camp is that they tend to be too short. As I said earlier, typically something like a week or so. And so all they can really provide is a brief experience with regards to programming. Another approach can be called the Intro CS approach. And in this approach, we have novice scientists and engineers take an introductory programming class in the computer science department. One of the benefits of this approach is that the students are able to learn from instructors who have done a lot of teaching in computer science, a lot of teaching to people who are novices to programming. However, one of the negatives of this approach is that the classes may focus quite a bit on syntax and computer science puzzles, and many times these classes will use languages that have limited use to scientists and engineers, perhaps most prominently the Java programming language. Another approach can be called the scientific analysis approach, and in this approach we ask the students to take a class on scientific data analysis and or modeling. Now, the hope is in this particular course, the students will also be introduced to programming, and oftentimes this approach may be paired with a little bit of the self-learning approach that we talked about earlier. One of the benefits of this particular kind of class structure is that the class itself, because it's focused on scientific data analysis and or modeling, provides built-in scientific motivation, so students can clearly see how the code that they write is translated into solving scientific and engineering problems. However, because the focus of the course isn't on teaching novices how to program, there's relatively little time that's dedicated for teaching the programming aspect of learning how to do data analysis and modeling. The scientific computing approach for a class to teach novices in science and engineering how to program is focused on teaching them in a class on scientific computing, that is, on numerical methods, etc. Here too, as in the previous case, there's built-in scientific motivation because the course is about scientific computing. However, here too, relatively little time is available for novices to learn how to program, and the use cases that are part of this course may also be too difficult for novices to be able to be comfortable with. A final kind of class structure that one can take to teach novice science and engineers how to program is to ask them to take an introductory programming course that's specifically designed for scientists. So in this particular class structure, again, there's built-in scientific motivation, and because the course is specifically designed to teach programming to novices, the pacing of it will be appropriate for novices. However, one of the problems with this particular class structure is that it highlights a need for resources that are written for scientists and engineers new to programming. As we discussed earlier, the kind of curricula that is available is, while there's a lot of it, is not necessarily geared for this kind of audience. People who are novices to programming, but also who are scientists and engineers. If we were to create a schematic where we plot on the x-axis the degree to which a class structure is helpful to novices, and on the y-axis the degree to which a class structure is motivating to scientists and engineers, and we plotted the different kinds of class structures we've just looked at on this schematic, we might have a graph that looks something like this. At the top we have the course and class structures that very intentionally try to connect with scientists and engineers. On the bottom are the class structures that don't do as well. And over to the right side, we have the kind of class structures that very explicitly try to reach the novices, and over to the left, the course structures that are less intentional in terms of that. Now, the one sort of outlier there is the boot camp, where the boot camp is very much trying to reach the reach novices, but it's just due to the duration of the boot camp, the fact that it's so short, that that kind of depth that novices often need in order to really get a firm handle on how to program, that's not able to be provided in that particular class structure. One of the other things that this particular schematic shows us too, as demonstrated through the coloring of the circles, is that for all these different kinds of class structures, they all have some or quite a few resources to support that kind of structure. The outlier is the yellow case for introductory programming courses that are geared for scientists and engineers. So while that particular kind of class structure both is motivating to scientists and engineers, as well as being helpful to novices, that particular class structure has currently few resources for students to be able to use. And so it's because there are so few resources that connect to novice scientists and engineers who are just learning to program that I wanted to close this webinar by describing a book that myself and my co-author team wrote and published with Cambridge University Press recently, called An Introduction to Python Programming for Scientists and Engineers. In this textbook, we tried really hard to pace it for the true novice, for the beginner, so that a novice could be able to learn programming confidently and in a way that really matches where they're coming from, that doesn't assume that they already know how to program. Yet at the same time, we wanted to write a textbook that enables the student to see very clearly how the programming that the student is learning can be used to solve science and engineering problems. Examples from science and engineering are used throughout the textbook, and we also include free Jupyter notebooks of programming problems in biology, chemistry, and physics to provide a lot of opportunity for the students to be able to practice. If you think such a textbook would be helpful to you, I encourage you to request an examination copy. Thanks so much for taking the time to listen to this webinar, and hope you have a great day.